creating a quantum circuit of 1 qubit, 1 classical bit, and this is another attribute what you may be used in order to rename your circuit. Okay, but there would be no problem, because once the object gets created in your hardware that is equivalent to the circuit, it would be uniquely identified by its own ID. Okay, it would not be remembered by the hardware that is at the back end of your that is classical machine, sorry, quantum machine, by the name of the circuit. So it's just because of our remembering purpose we may include this factor. So now this is remembering purpose we may include this factor. Okay. So now let's run this circuit. You know this template. We are just including what, that is air simulator we are using, and here yesterday in the yesterday's code we use the default constructor of air simulator. Now we are passing one argument here where the method is taken as an attribute which is initialized to a state vector, because we want to represent this thing into the state vector. Okay. Now this is the transpile, job run, etc., total counts, histograms, you all are known. Okay. So let me run this. So now you may see here that is a 1 we people are measuring for how many times? If we are running our code for 1000 times, so all 1000 times we are running. What does it mean to be? By default initialization of any quantum state is 0. So we apply the NOT gate, means it should be always there in a 1 state. So it is just demonstrating, okay, we are evaluating our NOT function. So now this is the corresponding vector. Okay. So in order to show the corresponding vector, we are taking here, the rest of the thing is same, only we are taking this instance, that is to plot the block sphere. Okay. So this will plot, or this will just show the block sphere. Now this one, understood? So basically we are known and directly we can do it. Okay, do it onto the IBM composer. So if you take the IBM composer directly, so your vector should be here after applying the NOT gate. Otherwise the vector should be at the north pole. Understood or not? Okay. Let's demonstrate in the other codes also. Now this is equivalent to the AND gate. Do you remember the AND gate circuit? How did we implement? Using Toffoli gate. Okay. So by using a Toffoli gate here, you just check it. I am taking a 3 qubits of quantum circuit and 1 qubit of classical circuit. Why? Because only the target qubit needs to be measured. Okay. We are interested in outcomes. Okay. Based on the certain inputs, what would be the possible outcomes? Okay. So now for the quantum circuit, and to realize the AND, we have taken this QC underscore AND as one of the object of the quantum circuit. Okay. And over which X gate is applied on 0. X gate is applied on index number 1 qubit, means the input what I am setting initially, it is 0 1. So for 0 1 the output of the AND gate is 0. Okay. So by default it is 0. So what to do? Applying this CCX gate. So CCX stands for controlled NOT gate, that is Toffoli gate. I discussed this thing yesterday. Okay. So now this is showing that 0 and 1 are the control qubits and 2 is the target qubit. Okay. Where we are applying our operation of NOT. So now what to measure? We have to measure the second index qubit. I told you already yesterday that everywhere there are the indices. We have to pass the indices. Okay. So the index number 2 is getting measured in the classical index of 0. Clear? So now after that one we are just plotting this circuit. So let's check this circuit now. The circuit we people are getting here as what? That is 1 1. So on 1 1, because the indices are passed as 0 and 1. Now after on both of these indices we have passed what? XS gate. So means my initialization is now at 1 1. So based on 1 1 the output of the AND gate would be 1. So let's check this is the plotting of histogram. Now the output 1, okay, we are evaluating for all the 1000 times. Now next let's plot the block vector. Now you see, this is the block vector. The left one is showing your index 0, this one is index number 1, this is index number 2, this is the target, okay. So once you have said that this is 1, this is 1, so based on 1 1 your output should be 1 because it's an AND gate. Let's change, otherwise let's change the input, okay. So if suppose I am not applying any gate, okay, on first qubit, okay. So now the input becomes what? 0 1, because the uppermost qubit, whatever we have written with the index 0, it shows the LSB, okay. So now at the LSB side we have set 0. So for 0 1 the output should be 0 anyways. So let's proceed again. Now here, what's the output we are getting? 0. So if the output is 0 means okay, as per our AND gate circuitry it is just returning us the output. Followed by, let's plot the block sphere. Now look at here, this is index number 0 and index 0 qubit is initialized to 0, index 1 initialized to 1, and AND gate output of 0 1 should be 0. So this is how you people may realize all the corresponding gates, okay. Now means all the different possible outcomes of the AND gate. Now let's proceed for the OR gate. So remember the OR gate, what was the circuit? Apply the C0, next C0, that is from the first control to C0, from the 0th index to C0, and followed by Toffoli, yes or no? So if you realize this circuit, so you just take it here, X gate is applied on 0, X gate is applied on 1, because this is OR. So just for OR I am just demonstrating, clear? Whether that this is the input setting basically. We are setting our input based on 0 1 1, okay. So now both are set to 1 1. Now this is the circuit part. This is the circuit part where the first index qubit is taken as control, applied a target to a NOT gate, okay. Now followed by again 0th index qubit is taken as control, applied target on the second. This is the Toffoli gate, okay. Once after that one, the target qubit needs to be measured anyways, okay. So now let's plot. This is the required circuit, yes. This part of the circuit we discussed, yes, okay. But the left side, the two NOT gates are representing the input settings. So we know based on 1 1 input, the output of the OR gate should be 1, okay. So let's check it here, that the output of the target is 1 now, okay. So now 1, so means the same can be visualized using a block sphere, okay. Now let's check for the other output setting. Suppose if both I am marking as, okay, means the inputs we are skipping, okay. So if we skip the input, so means this is the default circuit what we discussed, means both are initialized to 0. So for 0 0 the output of OR gate should be 0. So let's have a visualization here, okay. Output is 0 and let's check it here, the inputs, okay, they are set to 0 0 and the output is again 0. So you may check these all things by your own also. I will share the code files at the end of today's that is session, okay. So now let's proceed for XOR. You know now the XOR, yes. For XOR gate, what to take? That is for the different input it generates the output as 1, otherwise the output remains 0. Okay, so the first input setting what I have already taken as different. So on different one which we are expecting for 1. Okay, so let's run this one. This is the required circuit, already we have discussed yesterday. Now this should be the plotting of the histogram, output is 1. Okay, all 1000 times when I run the same circuit, okay, all 1000 times it is showing that 1 is measured, means there are no such noise remains present in this simulation. Okay, we can include noise also, okay, but noise simulation is also possible, but for just the beginning purpose you just let us know. Okay, you just check, this is what, this is 0, oh sorry, this is 1, this is 0. Okay, so 1 0, output should be 0, oh sorry, 1 output should be 1. So for because it is a XOR gate, if we have the same input, the output should be 0. So let's check, this is the circuit. Now what it is measuring, 0. Okay, 0 as the outcome, and let's realize here that okay, all are set to 0. So this is how, like, because this code contains all other files also, including of that is NOT gate, AND gate, NAND gate, OR gate, NOR gate, okay, XOR gate, XNOR gate, whatever we discussed, because rest of the codes are just would be the redundant discussion. You are all known that after applying that the NOT gate onto the last index qubit, we will get the corresponding results. Understood or not? So I think we should not just proceed, because already we have to cover the yesterday's time also in the today's session. Understood? Okay. So just let me finish with it. Okay. So now teleportation, if you may be able to see. Okay, look at here. Now this is the code related to a teleportation. Okay, so now you see, let me, is it fine? Fine, is it fine? Now this is the quantum circuit basically created, transpile, you know, plotting of histogram, AR simulator. Just based on the basic things you may create your the circuit of teleportation. What was the circuit? 3 qubits. Okay, between the second and third qubit create what? That is bell pair. Technically we used to call it as bell pair. How to create bell pair? Apply Hadamard on the second, control not on the second third, followed by go with the first qubit, apply control not, then followed by Hadamard, followed by that is two control operations, control X, control Z. Okay, so now the code is demonstrating in a reverse way of some classical entanglements. Okay, means after measuring the qubit instances, this code will check whether what is correctly measured. Okay, so there are two possibilities. Either you can directly code your circuit, I demonstrated yesterday, yes or no? Directly the circuit can be demonstrated, that is using Quirk simulation we have already taken. So this is another representation through which you can again get to know that how the circuit can be used for the purpose of teleporting our quantum information. Okay, now here the quantum circuit object is created based on circuit. Yes, so circuit is a name of the object here, and this object is created based on 3 qubits and 2 classical bits. Why 2 classical bits? Because only the sender qubits to be measured. Okay, so we always are interested to measure the sender qubits. Okay, and the last qubit belongs to a receiver, and it shows okay, when you perform the measurement on the sender qubit, the corresponding information would be automatically transported. Clear my point? So now, so here what to do? On the index number 1, because this is the initial position, on the index number, this is the Bell state creation, okay, between 2 and 3, okay, between sender and receiver. So at the index number 1 we are applying Hadamard, C0 we will be applying on index 1 and 2, followed by that is what to do, that is go for preparing your, these are, do not read the comment lines, so many comments I have already, this would be for your future purpose, okay, if you want to refer, you may refer, clear. So now this is only the target is 0th index qubit is control, and first would be the target, that is to create an entanglement of what? Of the input information that is having by the sender, okay, that wants to teleport, understood. Now followed by Hadamard. After that one, this circuit is initially measuring the information. Yesterday what we saw, that is first we apply the control NOT from 1 to, then control Z from 0 to, yes or no. So just this circuit is first doing what? The measurement. After measuring the required result, it will check classically that what is measured actually in the classical outcomes. Okay, based on that one, we will apply the reverse gates. Clear? So this can be also one of the possibility. So now we are just measuring 0th index qubit in a 0th classical bit and 1 index qubit in a 1 classical bit. Clear? Now after that one, this is checking of circuit. Okay, whether this information received at the 2nd index qubit, okay, means once you measure your 1st index qubit, and if it is 1, it is written already, that is when to apply the X gate to the qubit receiver. When to apply? If the classical bit 1 is already in 1. So if it is already in 1, then we have to apply what? The X gate. Similarly, if the classical bit is 0, okay, then we need to apply it as 1. So when you just draw this circuit, or let me, okay, this is the single cell, run this code. So this is how the circuit is looking like, okay. The yesterday's circuit what we discussed or what we already demonstrated using a quirk, now this is only reverse part. Reverse part is that in the yesterday's circuit we were directly doing, because everything were available in a visualization. Here, because we are simulating effect, we are just initially measuring the output, and based on the measured output we are just applying the NOT operations and Z operations, okay, but the operations would remain same again. Now after that one, we have to plot the histogram. So this need not to be discussed at all. So this is the plotting of histogram. This ensures, I already told you, when you measure the 2 qubits 0 0 0 1 1 0 and 1 1, there were the 4 different possibilities. Through any of the possible quantum state, your information is assured to be teleported. Clear my point? So the third instance of the qubit must always be a same quantum information what you wanted to teleport. Understood or not? So this is just a simple demonstration related to that one, okay. So now we should proceed to our other topic related to Grover's and phase estimation. Okay, listen first, that is important thing. It's time is around 10 o'clock, okay. So I would need around 1.5 hours to discuss both of these topics, okay. So we will have a tea break after just completing the topic only, huh? So just please do not interrupt me, kindly cooperate, okay. We are here to achieve a certain task. This is the task assigned to me, task assigned to you also, okay. So anyways, just try to cooperate in order to complete such a task, okay. So let's proceed with beginning of this. Yeah, this was the yesterday's load now, okay. So we have to still finish it up. So now look at this. So these are the two topics: Grover search, phase estimation. These are basically two different design strategies. What I am letting you know, you try to understand. If you remember, you all people belong to computer science now. It's okay, but I may let you know in perspective to computer science, okay. Or you try to understand. For every problem, we try to give our solution in the form of what? Algorithms, okay. Some methodology we use to propose, okay. Now for such an algorithm, we have some design strategies, yes or no? Like if you remember, that in a algorithm design we have the greedy method, yes, we have divide and conquer method, we have dynamic programming method, we have a branch and bound method, lower bound theory, so many different theories that we people may apply. Clear my point? So the thing is that if you are interested to design your quantum algorithm, so certain design strategy should be there or not. Okay, so I have the basic justification to use these two only, that is a quantum amplitude amplification and a phase estimation, as a basic design strategy for that is applicable in most of the algorithm designs. I do not say like this that only these two are using, understood, but most of the algorithmic designs are using these two, that is amplitude amplification and phase estimation, understood. So why these two are only required? You try to understand what I told you yesterday about the Hilbert space. That's a complex vector space allowing your vector to be measured in either in term of length or in term of angle. Okay, length means you may measure your amplitude, or angle means you may measure your phase. So either the phase related information you can get or the amplitude related information you can get. Okay, so for demonstrating these two things already we people are going for the Grover search and phase estimation technique. Other part is also available, that is called to be a quantum parallelism. Parallelism is one of the oracular based approach. We also revised yesterday in the form of what? Deuce algorithm, but you have already learned that Deuce part in your previous days. Okay, so you got to know that how your quantum parallelism can be implied in order to achieve the speed up results. Okay, so now let's hear. वो कहाँ है यार remote तुम्हारा चल रहा है? हाँ, so now what we will be the requisite background we will be looking for, and we have already covered, so no problem. Okay, so understanding the Grover search. Okay, how this Grover search would work and for what purpose it is applicable. Okay, now algorithm and its equivalent circuit we will be learning, followed by a phase estimation, its equivalent circuit, and the mathematics related to the Grovers and the phase estimation both. This is basically a bulky part. This is the bulk part for our discussion. If we do not discuss this one, means in half hour the topics would be over. Okay, there are no such things to be discussed. Okay, but this is the bulk, this is the load. Clear? Okay, now after that one we will have the demonstration of their corresponding implementations. Okay, and followed by the conclusion remarks. So these are the requisite backgrounds, we do not need to discuss, just look at here. This is the quantum design strategy. Okay, this is the quantum design strategy. Clear? So based on this design strategy, what we are calling for, that is here in quantum I categorized as based on our topics. Okay, that is to be covered during our workshop, that is FDP sessions, but there may be more different design strategies available, but these are the two basics: quantum amplitude amplification. So this is basically a design strategy, okay, through which you can be able to design your quantum algorithm. And quantum Grover search algorithm, that is a Grover's quantum search algorithm mechanism, is a dedicated algorithm, okay, that uses what? Amplitude amplification scheme. Understood? So this quantum Grover search would also let you know about the quantum interference mechanism. Okay, you learned about the interference, na? Yeah, learned, na? I also discussed the basic concept of interference. Whenever you expand your quantum system, there would be a simultaneous possibilities of multiple quantum states. Understood or not? And it means what? There would be a several overlapping of the quantum states. Okay, that leads to a constructive interference or destructive interference. This was the earlier example. If you remember, this is the example of interference. Yes or no? When your waveforms are likely in nature, their corresponding amplitude would be high. If they are just different to each other, their corresponding amplitude would be what? Negligible. Clear my point? So just because of that, these two, things this amplitude amplification scheme would let you know. Amplitude amplification, this is only the method, this method is going to demonstrate this thing, that how the amplitudes would be amplified. Understood? So now, and the second thing is, that is a quantum Fourier transform based phase estimation. So Fourier transform is another one of the approach, that is a design strategy that is used in another design of the another design approach. That is, this phase estimation is again a design approach, for which one we need a Fourier transform as well as the inverse Fourier transform. Two different transform schemes we need to learn. What are the transform scheme? You try to understand first. We usually deal with the time domain. Yes? Now by applying the quantum Fourier transform, we just shift our data from time domain to frequency domain. That's it. Okay. Here in the context of the quantum computing, you try to understand what we people are interested to do in. We are initially in a computational basis state, means in which state? 0, 1. Okay. On Z basis. Okay. Once you perform a Fourier transform, your quantum data gets transformed to what? A frequency domain. It means what? Your data remains in a circular basis. Okay. And in that basis you will have what? Plus, minus, plus I, minus I, and so many other possibilities. Understood or not? Okay. So there may be such possibilities related to the Fourier transform. But each of these topics, you just literally believe on me, each of these topics like Fourier transform, inverse Fourier transform, and followed by these two topics we can have what? The phase estimation approach. Okay. But we are scheduled with what? The phase estimation approach. But each of the topics, I am letting you know, each topic requires at least 3 hours of time to discuss completely. Okay. So it would be a bulk. So, but I will make you comfortable, you just try to understand the concept, what is happening here. Okay. And directly try to learn about the phase estimation technique. Okay. Now after that one, now this is the requisite here, that is to discuss prior to the algorithms. The first one, we know that the qubit can be represented as what? The wave function. Okay. This is the wave function of a qubit. Okay. So this is representing what? That the 0 and 1 are simultaneously appearing with their corresponding amplitudes A0, that is alpha 0, alpha 1. Okay. Where we know these alpha 0, alpha 1 are the complex probability amplitudes. When you apply the modulus square on that one, that would be equal to 1, because the summation of probability should always remains to 1. We know this thing. Okay. And this is the reason, because these are the complex amplitudes. Okay. So that is why we are applying this modulus operation. Otherwise there was no need of applying the modulus operation here. Okay. Squaring of the amplitude would be sufficient if you are only using the real amplitudes. Okay. Now look at here, the thing is uniform representation, non-uniform representation. We already discussed yesterday. If you remember, I told two types of superpositions can be created. First is uniform. Uniform means every quantum state be assigned with the same amplitude. Clear? Same amplitude. And in a non-uniform representation, the different quantum states can have different amplitudes. Understood? So now look at here. This is the uniform representation. This is the wave function over n qubit system. So for a n qubit system, like for a 1 qubit system, we have 1 by root 2. Yes. So for n qubit system, 1 by under root 2 raised to the power of n. If you put the value of n is equal to 1, if you put the value of n equal to 1, it would become 1 by root 2. Yes or no? And from I equal to 0 to 2 raised to the power 1 minus 1 means 2 minus 1. So the summation will go from what? The 0 to 1. So this would be what? I. So means 0 plus of 1 divided by root 2. Understood or not? So this is the basic mechanism through which you can have the uniform representation of your data. So the same state can be equally written as 1 by root n, where capital N is to be treated as what? 2 raised to the power of n. That is n to be written as capital N is equal to 2 raised to the power of n, where n is the number of qubits required. Okay. In order to explore this n number of different possibilities extent available in the system. Is it clear? So now, and the summation of their all corresponding amplitudes should be equal to, that is, the squaring of their amplitude should be equal to 1. This is as to justify the above statement. Now here the non-uniform representation. The wave function is same, I equal to 0 to 2 raised to the power n minus 1. You just observe. There is no such difference instead of what? 1 by root n. Because there is no such uniform distribution now. Clear? The states be associated with what? The different amplitudes. So now this is the way to represent the different amplitude. Alpha I along with I. Okay. So the state which is assigned with the amplitude. Clear my point? So every alpha I and their corresponding quantum state I can be a different one. We know the quantum states. We know the quantum state I because it is a summation which is going from 0 to what? 2 raised to the power n minus of 1. Understood? We know that. But what the corresponding amplitudes you are going to assign, that would be a tricky factor. And this such type of uniform, non-uniform representation be used actually in a machine learning mechanism. Okay, when you have certain data points and you want to encode that data points in a quantum states. Okay, so for encoding your data points into the quantum states, you may have the different amplitudes. So this is one of the encoding mechanism, and that encoding mechanism be called as amplitude encoding. Okay, so there would be several 8 or 10 types of around encoding mechanisms are available. Okay, out of which we will be also covering 3-4 mechanisms, that is, which are requisite. Okay, the rest of all the things we will not be covering because we are constrained with time. Understood? Now listen, on the uniform representation, this is the 2-qubit quantum state of the system. Okay, now that can be mathematically represented as, if suppose on the 2-qubit, what to write? 1 by 2 raised to the power 2, this loop will go from 0 to 2 raised to the power 2 minus 1. So it means what? 1 by 2 of 0, 1, 2 and 3. But this basically represents your what? Decimal system. This is the decimal number system. Understood or not? But if I want to represent my quantum state in a binary terms, okay, that is in a binary encoded format, means the state would be a quantum state, but representation is available in binary encoded format. So in that one, you just have a look here, the same wave function 1 by root 2 raised to the power 2. Now summation I have changed from I assigns the value 0 to 2 raised to the power n, means like this. We are writing like I, that should belong to a string of n bits. Understood or not? That is, this should belong to the string of n bits. So now n bits string, this should be assigned with the value of I. So now because of the superposition is still uniform, so the equal probability amplitude has been assigned like 1 by 2, the 0 0 0 1 1 0 1 1, and the corresponding amplitude square should be equal to 1. We know. Understood? Should we proceed? Chalo. Now come on to the topic of the Grover's structured search. Now we try to understand. First, just be clear with the unstructured database search problem. Okay, a data may be a structured one, unstructured one. Okay, but the problem is concerned only with the unstructured database problem. Okay, the proposer of this algorithm, the name is Log Grover. Okay, so he initiated this concern in 1996-7. Okay, so what was the concern is, at that time the people were using the telephone directories also. Yes or no? At that time. So I think you must be using that time also. So the people were referring to the telephone directory, and it is available in a sorted or no problem. Okay, if you want to just search your desired phone number for a particular person, so you go for the alphabetical ordering and search for the number. But what the problem he identified, in the same telephone directory, the data is sorted, okay, but he analyzed that if it would have been an unsorted database, then what would be done? Okay, like if somebody gives you a phone number, okay, I have the phone number, but I do not know this phone number belongs to whom? Okay, so how would you search? At that time, if you remember the size of the telephone directory in the earlier days, okay, and nobody have enough time in order to just go for iterations and to just look at the records, clear? Whether, and it was not to talk about the electronic record keeping system at that time, but anyways he observed, okay, if suppose you have such a record available in an electronic database also, so how would you be able to process? If you are given with the telephone number and I am asking that who is the owner of this number. So for such a perspective, initially he thought in a way like, is there any classical solution available? He said yes, the solution is available, but the solution is requiring a searching mechanism. So searching is available, but which search to be applied? That is sequential, no problem, okay, because no other mechanism available. Linear search we have to apply, linearly come down, turn down, pages, and if you find any search, stop. Otherwise, at the worst case, you will have to reach to the last of the telephone directory page and there is no problem, no such result found. So in order to just speed up this result in a that is a speed up format, okay, what he did, he thought about the amplitude amplification mechanism, okay, that is dealing with quantum algorithm, okay, that is interference. I told you, like if we have created a 4-qubit quantum system, 4-qubit quantum system means how many quantum states? 2 raised to the power 4, 16 different quantum state. Quantum state means it's a binary encoded form, you just assume at your side, 4 zeros to 4 ones, okay, these are the ranging of quantum states, understood? And now these all quantum states are relying in your system, in your quantum system, understood? Or otherwise take a very small example, 1 qubit, 0, 1, these are the 2 quantum states, both are available in your quantum system and it is causing interference pattern, yes or no? 0, 1, 0, 1, 0, 1, 0, 1, these are simultaneously occurring. Similarly, when you just expand the 4-qubit of system, so all these 16 possible different states are realized in parallel, means all are simultaneously available. So what he just observed, that if I have a mechanism, like I can explore the entire directory data into a superposition, okay, like yesterday we had one example of quantum RAM. What does it mean? Open book. In an instance of time, you have just read down the book, clear? Okay, so now with the similar context, he thought in a way that, okay, open entire directory into the RAM. If suppose entire data is available in a RAM, means in a single step of execution we can get to know, okay, the data is available, understood or no? At least this thing can be done, we can get to know, because if the entire data is available to us in a single step of execution, so we can get to know, okay, this is the telephone number that belongs to somebody. But for reporting that actually this telephone number is belonging to a particular person, we have to iterate the algorithm, understood? Otherwise in a single step of execution everything is done. But I told you, no such physical enough powerful quantum memory is still available. This is still one of the problem we are facing, understood? So what the people have done, so he just worked on one oracle, a black box operator he worked on, okay. So based on that black box, it is taking that only you try to pass what? Your phone number. So that oracle will take your input of phone number and it would check in a superposition of all telephone numbers, whether this telephone number is existing or not. If in any case that telephone number is found suitable, okay, or found in your database, so immediately their corresponding index would be negated. Understood or not? So negated means what? This is one of the reflection operation that is to be performed here in quantum. Understood? So what to do here, that once you get the index position of a particular item, you can go for amplifying the corresponding amplitude. Understood or not? Because for every quantum state there is associated amplitude. Understood or not? And if you know the quantum state to be amplified, means their corresponding amplitude we need to amplify. And why we are interested to amplify the amplitudes? Because if the amplitudes are high, so when you apply the modulus square on that one, you will have the better probability to measure your results. Like for a 1 qubit system, 1 by root 2 1 by root 2 is the amplitude assigned to what? 0 and 1. The probability of measuring the answer is 1 by 2, we know. But still I am not satisfied with half of probability, because it's a completely random chance. One time 0 is coming, other time 1 is coming, and we have already demonstrated this thing yesterday. Getting my point or not? So the fact is that if my target location is suppose index 1 or the quantum state 1, so the corresponding amplitude should be like 1, and the amplitude related to 0 should be what? 0, because summation of these probabilities should be equal to 1 anyways. So if the amplitude is 1 and you apply the modulus square on that one, so you will get 1 only. Understood or not? So that would be fruitful for me. So the same mechanism the people have used in the Grover search design. So what we used to call, that is for the classical brute force, it takes how much time? That is order of n. Okay, that is a linear searching mechanism over the entire brute force space. Okay, but the same task can be done here in order of root n time. But why root n? I'll let you know. Okay, why root n? I'll let you know. Okay, so the quantum operation, the operations which are involved here in a Grover's algorithm, it involves, the first is oracle. Oracle means a black box. Okay, so that oracle would perform what? Phase inversion operation. What it would perform? Phase inversion operation for a phase flip of the target state. Whatever the state is found, we will perform the, that is what? Flipping operation. After that one a diffusion operation. So diffusion is basically an amplitude amplification. The diffusion operator is basically an amplitude amplification operator, and this amplitude amplification means it is the possibility of realizing the interference mechanism. Those are the likely states. Okay, their corresponding amplitudes would be available in a constructive format. Okay, such that their corresponding amplitude would be enormously high, and the other amplitudes would be dedicatedly low. Understood? So now let's move here. So it's a design strategy, we know, completely based on the destructive and constructive destructive interference mechanism, because the amplitude here in the Grovers, only the diffusion operation is important. The diffusion is based on what? Amplitude amplification mechanism, means for realizing the interference mechanism. Okay, and the oracle is a dedicated oracle. Okay, this is based on your choice, means you are dealing, suppose the person was dealing with what? The person was dealing with the telephone directory. I also worked on that one. I applied the same oracle, okay, by modifying the oracle onto the biological sequence databases in order to find some DNA patterns. Understood or not? So we have to modify our oracle accordingly, such that a particular data items can be searched over a different possibilities of the unstructured database what we have in a real world. Understood or not? So the application perspective may be different based on your application where you are working. Okay, you may be able to design your own oracle. So what we will be discussing, we will be discussing the basic oracle. Okay, that how the oracle be constructed. Understood? Now, and we will take the advantage of the Qiskit algorithm also, that is the Qiskit framework, to directly realize our oracles. Now this is to be redundant to discussed here because we are known. Okay. Now this is the mechanism. Just look at here. This is the initial step 1. It shows what? If suppose we have 4 states 0, 1, 2, 3. So over these 4 states, this is the initial step. Step means this is uniform amplitudes. Okay. So these are uniform amplitudes. Okay. This is the first step. So because of this one only, uniform, non-uniform writing of the equations I discussed first. Understood? Now follow to that one, this is the step 2. This is the operation of oracle. So once the oracle is identified, okay, 2 we want to search. That is, our search element is present at what? The index number 2. Then we flip that index position at the 2. Clear? After that one, we compute the average around the mean amplitudes. Clear? So around the mean amplitudes means somehow like this is the amplitude, these 3 are plus amplitude, this is minus amplitude. We will compute the mean, and based on the computation of the mean value, we will have one formula to just strengthen or to amplify the amplitudes, like twice of mean value minus of previous amplitude. What is the formula? Twice of mean minus of previous amplitude. So when you observe or when you just visualize this thing, twice of mean, whatever the mean value is there, minus of what? Previous amplitude. So if you just observe here, for these, the values would be deducted. Wherever the twice of twice of mean value would be there, from that twice of mean, you are going to deduct the previous amplitude value. So these values would be deducted, yes or no? But for this only, you will perform what? Minus of minus thing. So minus of minus thing would be what? Plus. So only because of that one, you may see here, that is the state associated, that is the state of quantum state 2, and their corresponding amplitude is high, and in respect to these all, the amplitude is slightly smaller. And this keeps on continuing for root n times. It is not exactly root n because as per the asymptotic analysis, okay, we do not need to include the constants at all. Yes or no? We usually write order of n, order of log n, order of root n like this. But there exists some constants or not? As per the big O notation theory, some constant c must always be there. Yes or no? So that constant is also available here, that is known as pi by 4. Okay, so that pi value is also constant. Yes, by 4, that is 4 is also constant, and when you evaluate this one, this would again be a constant value. So that is why this is to be ignored. Understood or not? And we are only thinking in a way that the number of iterations or the rotations required for this algorithm would be root n. Okay. So when you keep on continuing like this, again we have flipped, compute the mean average. After that one, again twice of mean minus of previous amplitude. So now after some root n number of steps, you will have the possibility like the desired amplitude would be so high. This is the constructive interference. Okay. And there is a destructive interference pattern happening here with this one. Okay, with the other marked states. Understood or not? So this is just a flowchart related to what? The same step, that is this Grover oracle and diffusion, that is to be repeated for pi by 4 of root n time. And at the last, when this number of repetitions or iterations is done, you go to the index register and measure your index. Clear? So now let's proceed. This is the another mechanism. Okay, this is called to be a phase estimation approach. We will discuss one by one. Otherwise this would be fine, I think. One by one we should go, है ना? So okay, now the fonts are fine now. Is it fine? Now look at here. pen, yes, okay. Now, the Grover's algorithm works on what? Quantum amplitude amplification mechanism. Okay, so it is a design strategy that enhances or amplifies what? The amplitude to the desired item. Okay, whatever the desired item we have, we will be amplifying our amplitudes. Okay, everything is mapped in accordance to the, this is for the saving of our time. Okay, we have no time now. So now, this is a constructive destructive measurement, interference, we know already. Now, if you see that the Grover algorithm works in two parts. Okay, it works in two parts. Grover oracle, this is responsible for what? Phase inversion. That is a black box that is encoded with the marked item. Understood? This is encoded with the marked item. And the Grover's diffusion, which is inversion about the mean or inversion about the average. Okay, this is responsible for doing this task. Inversion about mean or inversion about average. And this task is basically used for the amplitude amplification purpose. Basically, amplitude amplification is a strategy. Grover's is an algorithm. So, algorithm is using what? That amplitude amplification strategy. Understood? Yes or no? Like, yesterday we discussed about Boolean knapsack problem. So, the Boolean, for a Boolean knapsack problem, we have the solution. Yes, but the solution is opted with which strategy? That is dynamic programming. Understood or not? So, in a certain mapping, mapping you try to understand. Okay. So, here the amplitude amplification is done, that is the probability amplitudes or the complex probability amplitudes are enhanced here, such that the probability of measuring the desired answer would be more. So, every time we will be enhancing. Okay. So, after completing certain number of rotations, pi by 4 of root n, we ensure that what? Our rotations are completed and now the amplitudes must be enhanced. Okay. Let us go for what? Measurement. Now, before proceeding to the actual mathematics related to the algorithm, you understand. We initially define x bar as our what? Marked item state, and we have this state in a superposition. We are assuming that whatever we are searching, that searching criteria is satisfied in what? In our quantum space. Means we have already explored. If suppose there is no search available, so that is to be declared again. Clear? That is to be declared that the search remains unsuccessful. Now, so the initial state, for the initial state mechanism, what we will be taking? We will be taking one register. This is one register initialized to 0, and this is written as tensor n. Tensor n means what? This is showing this is n qubit register. Clear? So, it is showing as n qubit register. Like, let us expand, like suppose we have 8 elements of database, very small. So, how many qubits we need? 10, that is 3. Okay. So, with the 3 qubits, all 2 raised to the power 3 means 8 different quantum states can be expanded. So, this is the thing here. So, like this is the initialization of the system. Now, you go with the wave function. Okay. And what to create here? Uniform superposition. What to create? And you know how to create a uniform superposition. How to create? Apply the Hadamard individually on a qubit. Remember, Hadamard is not a multi-qubit gate, it is a single qubit gate. So, for every qubit, you will have to apply the Hadamard. Understood? Once you apply the Hadamard on suppose n number of qubits, it would be assumed, okay, the Hadamard have been applied on all n qubits. Understood or not? Now, so Hadamard would be applied on 0 initialized quantum bits. So, it would turn your quantum state, that is 0 initialized quantum state, into what? 1 by under root 2 raised to the power n. This is the amplitude associated to your state, and from x belongs to binary string of x. Understood? So, in a binary encoded format, your all the indices of the database would be arranged. Like for 3 qubit system, from 000 001 010 011 100 101 110 and 111, all must be expanded. Clear? Now we are also considering that the state without or other than the X bar means what we are not searching. X bar is the searching element. So the other state which we are not interested in, this is also available in a superposition. Like, listen, what I know, I do not know anything about the quantum system. Once you have expanded, means we are completely unknown with that system, because it's a highly probabilistic system. Yes or no? How do you get to know? The system is not deterministic. Understood? So the fact is what? Once you have expanded your system, so this system must be containing your search element also and the other elements which are not suitable for the search criteria. So everything is available in your quantum system. Clear? Out of which our target is to identify the search, but the remainings are also available. Okay. So now here the solution state we represented as what? X bar. So for non-solution state we will be representing as what? Psi bar. Okay. So now this psi bar would be containing what? 1 by under root of 2 raised to the power n minus 1, means their corresponding amplitudes would be 1 by 2 raised to the power n minus of 1. Minus 1 is what? Because 1 is already shifted to the amplitude of marked state. Understood or not? Every quantum state is assigned with 1 by 2 raised to the power n, na? So if 1 we have already separated, so their corresponding amplitude to be separated, rest of the amplitudes would be, that is the summation of their corresponding amplitude would be same. Yes or no? So now here I am writing this x. X belongs to the binary state, but means end, it is written as end. X should not be equal to X bar. Clear? Means this would be a combination of all undesired states which we are not interested in to search for. Clear? So such a state superposition is also available in the form of non-solution state. Okay? So now how this algorithm works, you try to understand. Okay, this is a basic circuit related to the algorithm. You first try to understand the circuit. Circuit is simple because nothing is there. Look at here. This is the quantum circuit. We have to take n registers. Clear? That is n size quantum register. So this is the n sized quantum register we are taking. This is initial condition. At each qubit we are applying Hadamard. After applying Hadamard, what to apply? Oracle. So that oracle will perform what? Phase inversion. Means it would flip the target state. After that one, diffusion operation. So diffusion operation will perform the amplitude amplification task to check for the constructive or destructive interference patterns. Okay. Now after rotating these two tasks, means these two tasks to be iterated for how many times? Pi by 4 of root n times. Clear? So the pi by 4 of root n times we have to iterate the same task. Okay. After completing this task, we have to measure. What to measure? The register. This is the register. This is the index register. Like, listen, there are several different possible implementation approaches related to the Grover's algorithm. I am just letting you know about the simplest one to understand with only taking a single register. Only by one register we are just doing everything. Okay, we are assuming that in one register everything is contained. Okay, there can be a different possible designs based on your approach. Okay, you may modify the algorithm. Understood or not? Yes or no? Now, this is the shortest circuit that you can draw. This slash line is representing what? Number of qubits. It is written as n. So it is initialized, all qubits are initialized to 0. On all qubits we are applying Hadamard. After that one, on all the qubits we are applying the oracle. Oracle will perform the phase inversion followed by the diffusion operation followed by the measurement. That's it. Over. Clear? Now, corresponding to this one, you try to understand the mathematical aspects. Okay? These are the steps of the algorithm. Okay. If you remember the circuit, I marked here as psi 0, psi 1, psi 2. Okay. So only remember psi 0 is the initialized state. Psi 1 would be the Hadamard, means after uniform superposition. Psi 2 would be after phase inversion, oracle. Psi 3 would be after, that is diffusion. Clear? Now, and at the last we will be having a measurement, nothing else. Okay. So now what to do? This is the step number 1. Done. Step number 2. Creation of uniform superposition. It is done already. Okay, we discussed. Now, this is what? Oracle. Now, oracle, how to apply that oracle? This is a unitary function. It's a unitary operator. Okay. So that unitary operator, it would be a mixed state. Yes or no? So that unitary operator to be applied on the psi 1 state. This is the psi 1 state. And how this unitary function would work? You look at here. This is identity gate. I stands for identity. Identity over which? Over how many qubits? Over the same number of qubits what you are working. Understood? So this identity stands for identity gate over same number of qubits. Like for 1 qubit, the size of the identity gate operator is 2 cross 2. Okay, in 2 cross 2. Up now for 3 qubits, 8 by 8. So this must be the size of your identity operator. And in all diagonal elements, there would be 1. Okay, nothing else. Okay. Now, from I, what we are deducting, what we are just applying as a subtraction, that is twice of what this about? This is a solution state. X bar was what? X bar what? Solution state, what we are interested to search for. Okay. So what we are doing here, we are creating an outer product. This is cat bra. Yes or no? We are creating an outer product. So when you apply the outer product, so what should be the size of this cat? This is cat. The size of the cat is 2 raised to the power 3 cross 1 in our case. If suppose we are considering for 3 elements. So 2 raised to the power 3 cross 1. And the size of this bra would be 1 cross 2 raised to the power 3. So again, one inner order remains same, outer order matrix we will be getting, means 2 raised to the power 3 cross 2 raised to the power 3. The operators are same. Yes. So if the operator size are same, then we can apply this minus operation. The matrix orders are same. The plus minus can be directly applied. Yes or no? So now we are applying the minus operation. So wherever the element would be marked, because this is what? The mixed state of the marked state. Yes or no? It's a mixed superposition of what? Marked state. So whatever you want to mark, that would be marked with the negative factor. This is a negative factor, I minus of marked. Clear? So whatever the element you are going to mark, their corresponding phase would be initialized to minus. Phase initialization means what? Yesterday we have worked on the phase operators. Z gate, S gate, T gate. Remember? Yes or no? Basic Z operator you may apply here in order to just flip your phase. Clear my point? Yes. And this should be applied if your quantum state is remaining in state 1. Understood or not? And you are just passing this one here. Clear? Now, so it means what? Your unitary function would work like in a way that if your quantum state is not belonging to the solution state, it is not belonging, okay, then do nothing with the quantum state. But if your quantum state is equal to the solution state, that at that time, what? Perform the phase inversion. That's the simple approach, nothing else. Okay. Now, what to do next? Come to the Grover diffusion operation. Okay. Come to the Grover diffusion. Now, what the step? This is the main step. Okay. Irrespective of the oracle construction. Now, what this diffusion is doing? This is U perpendicular. Okay. So now amplitude amplification would be called as what? Inversion about the mean value. So we have to compute the mean value, and followed after that one, based on the mean value, we have to again recompute the amplitudes. Okay. So now what this operator is defined? Twice of psi, where what is psi? Psi is a wave function. It's a superposition. Superposition of what? including solution state and non-solution state. All are contained in that one. Clear? So we will be expanding our superposition of all the quantum states, okay, and from which we are just negating what? The value of I. Okay. So with that function means how this oracle, how this unitary function work, these are the two that is steps through which, because you write it like in a mathematical operations, okay, means these are the mathematics or the matrix operations, okay, but their corresponding operation would be looking like this. This is the mean value, A bar, what I am taking? Mean value. So this mean value will be computed based on what? 1 by n. N means number of elements contained in a database. Suppose we are working for 8 elements, so this n value should be n. Otherwise you may write down 2 raised to the power 3 also, where 3 must be the number of qubits required. So whatever you use, you may use, because I already told there. Okay. So now, so 1 by n, because of the taking the average value. So 1 by n summation of x, because x is the state which is working on what? Working on the quantum system. Yes or no? Because these all quantum states are contained within the quantum system. So now this x assigns the 0 to n minus 1, always go to compute what? Their corresponding amplitudes. These alpha x is representing the amplitude. You take the summation of all amplitudes, okay, divide by n, assign it to what? Mean value or an average value, then go for recomputing the new amplitudes, okay, and that recomputation of the new amplitude would be what? Twice of average minus of previous amplitude. That's it. Okay, you try to understand here. Do we have duster? Duster नहीं है? चलो ठीक है, ये बोर्ड तो खैर खाली पड़ा है, इधर से निपटा लेना. Look at the board. Now what is happening? Suppose let's expand. Let's expand our system. Okay. इधर से ले लेता हूँ. Thank you. Now look at here. Let's expand our system. If suppose this is representing amplitude, this is the time domain now. Okay. Now let's work for 4 states only. Okay. So for a 4, like this is 4 elements database I am considering. Okay. This is index number 00, 01, 10 and 11. Okay. And I am interested to search for an element. That element is supposed to be located here, okay, at the index position 10. And this is the responsibility of the oracle. Oracle has to mark, okay, anyways. Okay, this is the target element. Means if the element what we are searching is, if it is located at this location, means we have to report this location index. Understood or not? So our target is what? 10. So 10 means their decimal equivalent is what? 0, 1, 2, 3. But write in cat, because the information is different. Clear? There are no such 0, 1, 2, 3 available in our system. Clear? So now this is 0, 0. Suppose this is 0, 1, this is 1, 0 and this is 1, 1. So when we apply what? Uniform superposition, means the Hadamard on the 0 initialized qubit. Initially the amplitude should be 0. Yes or no? Initial state, the amplitudes of all these states should be 0. Nothing is there. But once you apply the Hadamard, there would be an equal probable superposition. Yes or no? So the amplitude should be same for all. So like I am writing here, that is for 1 by 4 would be 1 by 2. 1 by under root 4 means 1 by 2. So this is I am marking here as 1 by 2. So every of the quantum state is assigned with what? A same amplitude here. Understood? After that one, we have to mark. What to mark? That is a target state. If suppose I am considering that this is the target state, okay, so this is suppose my target state, so I am writing here this is 10 and this has been, and this has been now marked with what? That is the flip operation. So it becomes what? 1 by 2. So plus 1 by 2 will become what? Minus 1 by 2. Now after this step, where we are coming to perform the diffusion operation. So diffusion will do what? Twice of psi minus of I. Okay. So how this step be computed? सबसे पहले what to do? That is compute the average. So how do we calculate the average? 1 by what? N. So 1 by n means, okay, I am taking the denominator as 4, okay, because total number of states are 4. What are the amplitudes right now? 0, 0 amplitude is 1 by 2, 1 by 2, this is minus 1 by 2, this is plus 1 by 2. So I am writing as 1 by 2 plus 1 by 2 minus of 1 by 2 plus of 1 by 2. Yes? Minus 1 by 2, 1 by 2 gets cancelled. Half plus half, 1. So it is what? 1 by 4. That's it. So we have obtained our what? The average value. Now the mean is calculated. Average is calculated around that is for the amplitudes. Now based on that mean value, we have to compute what? The newly updated amplitude. So if now the previous amplitude is supposed to be alpha x, so now the updated would be alpha prime. Okay, so that should be what? Twice of a bar minus of alpha x. Clear? Where x is the state belongs to the superposition. Clear? So now let's calculate what to calculate for alpha 0 0 prime. And this would be same as alpha 0 1, this would be same as alpha 1 1. Yes, so I am writing here alpha 0 0, alpha 0 1 and alpha 1 0. They all will become same. Okay, so what to write here? That is twice of what is alpha? Alpha is, what is average? Average is 1 by 4 minus of 1 by 2. Okay, so because this was the amplitude earlier calculated, so it is what? 1 by 2. 1 by 2 minus 1 by 2, it is equal to 0. So at the first step only, the amplitudes related to the non-desired elements have now become 0. Okay, now let's check for what? The desired element 1 0. For 1 0, what to write? Twice of 1 by 4 minus of 1 by 2. So this minus would be plus. This would be what? Half plus of half. Yes or no? So half plus of half would be 1. So after the first step only, if we see that this is the amplitude, this is here the time, now the amplitude associated to 0 0, 0 1, 1 0 and here 1 1. So the target is suppose like this. And what about the amplitudes of what? Amplitudes. And as per the root n factor, as per the pi by 4 of root n factor, can you be able to calculate how many iterations we require? Pi by 4 of root n under root n, yes, pi by 4 of root n, can you calculate? Under root n is 2 root 2, that is under root n is under root, here in this case it is under root 4 would be what? 2 and 2 and pi by 4, so pi by 4 it would be 1.72 around. Okay, this is 3.14, 1.56 around, 5677. Okay, so when you multiply this, when you divide this, so what's the value you are getting? 1 point something. So around 1 number of rotation is still required to just get your desired answer. So in a single step of execution, you have marked your item here. Okay, your item is now marked with the highest amplitude, and if the amplitude is available to you, means we are not to be bothered about, only go for measurement. Clear or not? Now, so after that one, what to do? Perform the measurement of index register. So once you go for the index register measurement, everything would be over. Clear? Is this clear? Now, these are the mathematical representations of the operator. You may note down. What was the UF? What was the UF? I minus of twice of psi bar, that is cat bra. Okay? I minus of twice of cat bra of solution state. Yes or no? So that operational matrix can be written down as like this. Like if you see here, unitary function applied on a quantum state, there would be a function f of x. This f of x function would compute or would check whether your marked item is available within the quantum state of the system or not. Yes or no? So if it is there, so this function would be evaluated. Look at here, this function would be evaluated either as 1 or 0. When this returns 1, when your quantum state is same as what? The desired state. Okay. And if your quantum state is not same as desired state, at that time this function returns 0. Means suppose for 0, 0, f of x should be 0. So something to the power 0 means it is 1. Means 0, 0 will remain 0, 0. Yes? Similarly for 0, 1, f of x should be again 0. So again 0, 1 would remain 0, 1. But what about 1, 0? If you take 1, 0 here, that f of x, because it is equal to the desired item, this would be evaluated to 1. So once this gets evaluated to 1, yes, so this minus 1 factor be associated with what? 1, 0. So this is the operational mechanism what we have already discussed. Yes or no? Clear? Yes? Now, one minute, huh? क्या हुआ? अरे यार ये इससे कैसे आएगा? चलो ठीक है. So this is fine. Now look at here. Look at here. This is how do we write this unitary function? And all diagonals, because what you are doing, I minus of twice of that is psi bar, x bar, and both are available in cat bra. Means it's an outer product. Okay. So the same size of matrix is there. So in that matrix, in all diagonal entries, this function get associated with that diagonal entries of minus 1. If suppose this is for 4, okay, so whatever the third row is there, third row means that should belong to 1, 0. So at that 1, 0, this function of 2 would be evaluated to 1, and at that time this minus 1 factor gets associated. This is matrix operation. So you may do, because doing matrix operation it relatively will consume more time. Understood or not? Now this is the diffusion operation. So what the diffusion operation is doing? It is calculating the mean, and based on the mean value, it is what? It is updating the newly computed value. What it does? It does twice of psi minus of I. Yes or no? So this is how the 2 by n factor gets associated with each of these states. If you only observe this diagonal entries, okay, so that would be what? 2 by n minus of 1. This would be a mathematical factor associated to each one. Clear? Otherwise for all the relevant entries would be 2 by n. Understood? Yes? So this is the simple way to understand our Grover's part. Okay? Now have some geometric interpretation related to the Grover's. Geometric interpretation. Okay? Now you know this is what? Solution state on y-axis. Okay? It is 2-dimensional structure right now. The block sphere is 3-dimensional. Okay? The things are, too many things are complex. Okay? We usually try to understand the thing in a 2-dimensional plane, then switch it over what? Over the 3D mechanism. Okay? And now again to interpret the result, we try to map the 3D block sphere mechanism onto the 2D sphere. Understood or not? What I wrote down, the generalized equation of psi, that is alpha 0 of 0 plus alpha 1 of 1. That's it. But if suppose the same equation I want to write onto the block sphere, so what should I write? that is that same wave function would become what? That is cos theta by 2 of 0 plus e raised to the power I phi sin theta by 2. Okay, so the thing is that why this theta by 2? Because again we are mapping from a 3 dimension to 2 dimensions. Because if you see, when we see that the quantum states remains orthogonal to each other, in a 2-dimensional perspective what we know, in a 2-dimensional perspective means 90-degree angle means they are orthogonal. But here at the Bloch sphere, the 0 state remains at north pole, 1 state remains at south pole, and if you see the phase difference between both of them, it's a 180 degree. Yes or no? So the problem is complex here to understand always. Getting my point? Are yes or no? 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 Acha, it's okay, ma'am. It's okay. Chalo. Chalo, it's okay. So now this is the solution state. Okay? Basically it is showing your amplitude, highest possibility of the amplitude. So highest possibility of amplitude means what? If suppose your quantum particle is just working on like a wave, okay, so what's the maximum amplitude related to your sine wave? That is 1. Yes or no? So if we are considering for the value of 1, okay, so when we will be reaching to that 1 value, when we have the value of pi as divided by 2, that is pi by 2, so we will reach definitely there. So our target is what? We are expecting our solution state, that is the amplitude to be there at the y-axis with the highest one. This is my desired expectation. Okay, I want that whatever the amplitude is there, that should be aligned to the y state. Okay, axis. Now what is available on x? Psi bar. Psi bar was all quantum states which are not the solution state. Understand or not? So this is the initial expansion. We have non-solution, this is solution. This is expectation, this is non-expectation. Okay. Now, but when do you create the quantum system? When you evolve the quantum system, so this evolves like this. This is the psi 1 state. This is the first. Psi 0 is what? Psi 0 is 0. This is initialized. But when you apply the Hadamard, means it creates a uniform superposition. So this is the uniform superposition gets created with certain angle. Getting my point? So if the uniform superposition is created, means this uniform superposition state contains solution state as well as non-solution all with certain angle. So what we need to do initially among this solution states, means among this superposition of state, whatever our desired item like this, okay, it has to be reflected here. So what we perform, this is the UF operation. This is the reflection operation. We have just negated the phase. This is the transition. Okay. This is what? One transformation. You may call it as reflection. Okay. It is just a reflection operation what we have performed. So once you perform the reflection using that oracle operation, your desired item would be negated and it is available here. After that you compute the mean. Clear? After that you compute the diffusion mean, and with that one you again update your amplitudes. So this is a mechanism related to the diffusion operation. So based on that diffusion operation criteria, thus again every amplitude gets shifted. Okay. So now when you perform that shifting, so this is what? U perpendicular, that is working on, that is U psi working on what? Oracle, that is applied on psi 1. So this is UF on psi 1 over which we have applied this diffusion operation. So means the same state is now reaching towards this. Now if you observe, this y-axis is showing what? The height. Yes, this is showing only the height. Yes or no? Initially the height was what? Like this. Yes or no? Whatever it is. Like suppose 0.5. Okay, like in our case it is 0.5 now, 1 by 2. Yes or no? But now at the next state, it is now becoming like suppose 1.75, now increasing. Okay, because after one iteration we got our result with 1. So this is an exceptional case for the 2 qubits of grower. Getting? So on that special case, only after one iteration this state initially shifted down to what? To this Y state. So means this amplitude what we are expecting after this has been aligned to the Y state. Understood or not? And once your amplitude got aligned with the Y state, means you may measure whichever the amplitude available at Y, means with the that would be the maximum probability to measure your answer. And if you are measuring your answer with the probability 1, means although you are dealing with the highly probabilistic system, but you are measuring your answer with the 100% accuracy. Means you are approaching towards what? The deterministic answers. Yes or no? If suppose you are getting your answer as with 0.5, so still there is a dilemma whether the 10 was the marked state or it was not the marked state. But this happen when you run the same algorithm on the real machine. So this would happen even though you are marking 10 as a quantum state, but sometimes other states will also be measured. Why? Because of noise remains present in the system. This may happen, but yet just do not expect a lot of errors to come there. Okay, it would happen like if you run the same algorithm 1024 times, so out of 1024 times, 24 times it could happen. Yes or no? For 1000 times you will get the same results. Yes or no? This is for the still the scientists are working for the development of the noise resilient quantum system. Okay, but still we are in an era of NISQ. Okay, all the machines are NISQ based. Understood? Yes or no? Is it clear? So now it's up to you whether you are interested to go with the demonstration first or we should discuss the phase estimation approach first. I think demonstration would be initially required because it would completed it would be completed in within 2 minutes of time. Because now you are in a connection. After 15-20 minutes if I ask you, means you will have to just think upon okay what was happening there at Grover. So let's move down. Now look at here. What's the time? 11? 10. So it's okay. 11:30 I am targeting, but 5-10 minutes I think it would be extended. But anyways, you are requested to cooperate. Now listen, it's a cascade implementation of the Grovers. These are the importing of libraries. But here this implementation is specifically taking quantum register, classical register. This is only for the purpose of knowing whether you may also take classical register, quantum register separately. Till now what we did, we directly created the quantum circuit by passing what? The arguments. First argument is specifying the size of the quantum register, second is showing what? The classical register. Right now what we will be doing, we will be initially taking the quantum register separately, classical register separately. Now instead of passing 1131 or 32 like these values, we will be passing these names: quantum register, classical register. Clear? So now rest of the libraries are same, but only this is to be discussed. This is what? From the Qiskit circuit library. Qiskit you have already imported and it would work, no problem. Okay. So now from that one what to import? That is MCX gate. I told you yesterday if you remember. Multi-controlled NOT gate. Yes, I told you C0, CC0 as well as the Qiskit is supporting multi-controlled NOT gate. So this is a multi-controlled NOT gate operator. Okay, and this is required. Why? Because of the diffusion operation. So I will let you know that why it is required in a diffusion operation first. Okay, you look at here. This is the design. This is the design of the diffusion operation. Can you be able to see? Look at here. Just this is the design of the diffusion operation. You look, whatever the index register you have, very simple to design. Look at the board. What to do at the first layer of the circuit? This is to be called as layering circuit. Okay, this is available in layers. All gates are attached in layer. Layer 1 all Hadamard. Layer 2 all X. Layer 3 target qubit is assigned with H. Understood? Yes or no? Yesterday we saw one parameter of what? That is quantum machine. CLOPS. CLOPS means circuit layer operation per second. And we saw 180 kilo means this much amount of circuit layer operation is supported by the machine. So you think upon the speed of the machine. That is why it only takes 1 second of time in order to execute. And they are intentionally consumer time. Otherwise it would have been taken around some milliseconds of time or nanoseconds of time to just compute your results. Getting or not? Because they have assigned you the timers of 10 minutes. Na? So anyways they are consuming your time. Clear? So now look at here. So this is the simple design. All Hadamard followed by all X followed by H. But if you see the last one, this is what? H, X, H. This is equal to what? Z. I told you yesterday, everything is intentional. Nothing, I do not discuss anything like in a vague manner. Clear? But I try to connect. But it takes time. Yes or no? We cannot have food for all times at one place. Yes or no? For like breakfast, lunch, dinner, snacks, everything. We cannot eat for a single moment of time. Yes or no? That is why the different times are allotted. So similarly, now it is the time to realize these things. Yes? So now after that one, means this is the phase. Now after that one, what? This is a multi-control NOT gate. So multi means n-1 number of qubits would be the control, this would be the target. And whatever the circuit we have on the left hand side, the right hand side would be also having the reverse circuit. Reverse circuit. Understood or not? Now, in the practical implementation of the Grovers, we would use one operator. This is known as the operator, importing of operator. This is operator. So this operator is basically a class. Okay, so this class is contained in a Qiskit.quantum information. And why I am using this class, like for 4 qubit element, sorry, for 2 qubit element, how many quantum states I took? 0, 0, 0, 1, 1, 0, 1, 1. So I am here to demonstrate the same thing. Okay, 0, 0, 2, 1, 1. And what is our target element? 1, 0. Okay, so the operator class is giving us the privilege to directly create our oracle. Means we have to mark our desired element. On behalf of us, it would implicitly create the oracle. Okay, so this is the simplest approach what I am letting you know now. Okay, there can be a complex approaches. Okay, but it would be dedicated towards your work you are going on. Okay, so now look at here. Rest of the things you are known, nothing to be discussed. This is the operator. So this operator class is passed with what? With some information. What's the information it is? It is 1 0 0 0 1 1 0 0 0 1 0 and 0 0 0 1. This is nothing but it is written as same what these states are. How do we write these states as a vector? This is what? Index number 0. This is index 0. Yes, so index 0, so at index 0 put 1, rest of the qubits are 0. This is index number 1. So index number 1 means this is index 0, this is index 1, rest of the qubits are 0. This is what? Index number 2. This is index 2. So at the second position you put 0, 0 and 1 would be, rest of all are 0. This is what? The last one, that is 0, 0, 0, 1. Are you getting the same on the operator matrix? Yes. But on that operator matrix, I have not marked any element. Nothing is marked. I am considering, okay, this is my default system. Okay, so let's see at the end first, because if you have the default system, you are not interested to search anything. So what would happen in a system? There would be a equal probability distribution, yes or no? Everything would be available, like with their corresponding probability, yes? Like what's the probability? 1 by 4, yes or no? 1 by 2 is the amplitude, so square modulus square would be 1 by 4. So 1 by 4 is the probability of associated amplitudes, yes or no? So now let's proceed. So this is, so let's run as one by one. Okay, first cell run. Now this is the unitary function. Let's check. Run. Okay. Now we are printing this unitary. So this is the state vector information. Okay. These are the state vector information. Means basically we used to write like this 1 0 0. But these are the complex amplitudes. Yes or no? So the complex numbers you are dealing with. Every like this 1 0 0 is written as 1 plus 0 plus 0 dot j, 0 plus 0 dot j, like this. Everything is represented. Clear? Now this is what? Quantum register. So quantum register is a class. Now the constructor is called with what? We need 2 qubit of register and giving a name as Q. So this is a renaming operation. If it is not mandatory at all. Now classical register on 2 qubits. Clear? Now we are assigning as QRCR. Now based on that QRCR, here is a direct written. Clear? So it is up to you whether you are using or not. And if you are already known that you need only 2 qubits, so why to use quantum register and classical register? But this is only for demonstration method, that if you want to write any generic codes, so for generic codes we need not to modify at all time. Clear? So we always try to maintain some generic settings. Clear or not? So only you will have to change about the quantum register size and classical register size, nothing else. Now, so the Q circuit is now the instance of the quantum circuit that is assigned with 2 2. Now on the Q circuit we are appending here. This is append is a function. This appending function is appending what? U2. What was the U2? It was the unitary operator that is created on behalf of operator class instance. Means these all vectors are available in that unitary operator. So we are assigning that unitary operator on what? The quantum register. So it is an append operation. Clear? After that one, for I in a range on the length of the quantum register, everything to be measured. So initially we are just checking, okay, the things are encoded or not, the things are appended or not, okay. And after that one we are just plotting our unitary. So this is the unitary. So this unitary is contained what? This is containing these 4, 0 0 0 1 1 0 1 1, okay. But you are only be able to see the unitary. The implicit functionality of the unitary can also be checked when you design the oracle. Right now it is basically, we have not marked anything, na? Did we mark anything? No, because we are not interested in search right now. I am just iterating. When you mark a particular element, this implicit functionality of the unitary will also be shown to you. Clear? Now, after that one, this is the decomposition. Decomposition of what? Decomposition of the oracle. Okay. So let me check. There is nothing decomposed. I told now we have not marked anything. So unitary is basically showing these vectors. Okay. And this need not to be shown because it is implicitly coded. Now after that one, this is to check whether every unitary, because every unitary operator should be a reversible operation. Yes. So let's check whether that U2 is a unitary or not. It is true. The Boolean operation it is returning. Now after that one, number of qubits, again 2, because we are working on that one. So now based on that one, now the quantum register based on number of qubits is created on QR. Classical register based on the same number of qubits assigned to CR. Now the quantum circuit is created based on the QR CR. This is again the initialization. Clear? The quantum circuit is available. Now on that quantum circuit, what to do? This is the first step, psi 1. Can you be able to see psi 1? For I in a range of number of qubits on the circuit, append Hadamard on each index. Yes? So at each index the Hadamard would be applied. After that one there is a specific function of a barrier. Okay? That is to separate out your quantum circuit states. Okay? Like your quantum circuit portions can be separated out. So the barrier can be applied. Okay? Now after that one, go to the oracle operation. So that oracle is simple one. On the same quantum circuit we have to append the unitary based on same quantum register, because the unitary would be applied on quantum register. There is no need on classical one. Clear? So because we have not marked anything, so this would remain same. Now after that again barrier. Now this is the step of diffusion operation. If you remember the circuit of diffusion, what was the all Hadamard, all X followed by target Hadamard followed by multi-control NOT gate and reverse circuit. Diffusion circuit I am talking about, okay, in a layered operation. So you just check it here. क्या हो गया यार? कुछ हिला है क्या अभी? हाँ, it's okay. Now, look at. So this is what? Applying Hadamard on all layers. Yes? Applying Hadamard on all qubits in a range of number of qubits. After that one, apply X on all qubits. After that, apply Hadamard on which qubit index? Number of qubits minus 1. If number of qubits are 2, so 2 minus 1 is 1. So 1 is the last index in 2 index. Yes or no? If we have only 2 indices, so 0 and 1. So 2 minus 1 should be 1. Okay. After that one, this is the multi-control NOT gate. So it's a class now. The constructor is called between the number of qubits minus of 1. So this would be taken as what? The control 1. And based on this multi-control NOT gate and the list in a range, this is showing your the number of qubits. That is control qubits. And after taking this number of control qubits, this portion would be just showing your target one. Okay, on which the NOT operation would be applied. After that one, if you see, because this multi-control NOT gate is also appended on the same circuit. After that one, this portion is the reverse of the circuit. Last gate means Hadamard, last wire is Hadamard followed by all X followed by all H. Done. After that one again a barrier is available and we have to measure the index register, and index register is available with 01 and it is to be measured in 01 classical register. Clear? Is it clear? Let's draw the circuit. This is your entire circuit now. Can you be able to see? This is my first step. This is what? Unitary oracle. But oracle is looking like nothing. Okay, because we have not marked. Okay, but this is diffusion operation followed by measurement. Okay, so this is happening. So now when we go for simulating on these two results, okay, so let's, because this simulation is a template code, so nothing to be discussed. Now see, 0 0 0 1 1 0 1 1 all are available, and as by visualizing this one, I can get to know, okay, I think 1 1 would be my marked state, because their corresponding amplitude would be high. But it is not like that, because we have not marked anything. Clear? Now let's come to the top, okay, and see the simplest approach to implement this oracle. Now, which state we marked here? 2, okay. So this is vector of 2. This is vector of 2. Let me mark it with minus, okay, and let's run all cells, because we need to run all the cells from top to bottom, okay. Now you see, this is the functionality of your oracle. This is the oracle. Earlier it was unitary, yes or no? Now it has encoded directly. It has encoded this oracle into these unitaries, and this each of the unitaries again available in certain phase rotations. If you may see, these are some angle values, okay, and this is the complex representation of every unitary, okay. So we people may only be here to realize what, that okay, the grovers can be implemented, the things are available, but when you go for a specific problem, you will have to design your own oracle. This is the task, because if you thinking upon from some research perspective, so what should be your contribution otherwise? If everything is available, so there is no use of, clear or not? So now look at here. Now in the below code everything is run. Now this is the unitary directly showing, okay. Now here for 1000 number of times, what is measured? 10, okay, because that 10 is marked state, and 1000 times means because it's a simulation. If it would have been a real machine, all 1000 times we can't expect. Understood or not? Is this fine? Fine. So should we just switch it towards the phase estimation approach? Chalo, let's proceed towards the phase estimation. ब्रेक लेना चलो ले लेते हैं मैडम, ठीक है, 5 minutes. हाँ, that's it. Because we were searching about 10, so that is why this 10 is remaining present in the system. Its corresponding amplitude is 1 na. Rest of the amplitude are 0. If suppose the amplitude possibilities were there like 0.25 or something for others, so they must be measuring. But in our case, for a special 2 case, so what you will have to do in the same code, you will have to expand the operator matrix for 3 qubit system, 4 qubit system, 5 qubit system, and to see the results. Okay. Accordingly, it will construct that result. 5 minutes, bhaiya, 5 minutes, please. Because we are limited to what? 4:30.
How to find the amplitude of a particular state?
This is the amplitude.
Here we have calculated the amplitude of each state. How to calculate the amplitude there?
Means you want to get the amplitude detail. So for getting that amplitude detail, like you assume from the first qubit system, that is 1 qubit system. What is the amplitude? 1 by root to 1 by root. है ना? So in order to get the amplitude value, okay, you have to measure your answer. Whatever the answer you are getting, their corresponding root value must be the amplitude. Means you are measuring your answer with the probability. How much is the probability? 50%. Suppose 1 by 2. So their corresponding amplitude will be under root of 1 by 2. Because under the evolution of the quantum system, we can't be able to see anything. On a completely or हाँ measure करो उसके बाद उसकी root value पता कर लो. So that must be the amplitude. हाँ, yes sir. Madam, can please ask somebody to just bring tea.
Yes, sir.
Acha, okay. Okay. Yes, sir.
So how can I apply this Hadamard on this?
This is simple, sir, directly. This is Hadamard means you are applying directly if you are writing it wrong. Header mart is what?
Yeah.
Header mart is single qubit gate, sir.
Yes, sir.
You can't apply on the 3 qubit system. This is writing is wrong. Okay, you may write down like,
3 bits
so you may write down like this. Okay, header mart you are applying on 3 qubits on this state.
Yes.
So when you apply the header mart on this state, so this would be separated like this. Header mart is applied, suppose. So when you apply the header mart, so this would become what? 0 minus 1 by root 2. This would become what? A tensor. It is a tensor operation because tensor you have written down. Okay. So it would be what? 0 plus 1 by root 2. This is tensor with 0 plus 1 by root 2. Now, this 1 by root 2 will become common and you just apply these tensor of values. Okay? Tensor of value. There would be 8 different possibilities. 3 qubit, 8 different. 8 different.
For any gate, we should do like this, sir.
What?
For any gate.
For any gate, yes. Like if you are applying X gate also, so X you will apply like by writing a tensor. Without writing tensor, you can't apply because these are the single qubit operations. Na?
Yes.
So how we will be applying on the multiple number of qubits? No possibility. Okay. Actually, in the morning, I sat on my so the alignment completely. So that is why there is a headache in my mind right now. It is not completely aligned now. I worked hard to just make it aligned.
Let us put it on the table and adjust it.
No, I tried, sir. I tried about 5-10 minutes, but I lost like here, like there is a gap. This is after that one, means after finalizing my fix. Actually, there is a headache right now.
Otherwise, you can adjust it after wearing it.
I am trying.
विजन में तो कुछ ये नहीं है
No, vision में problem नहीं, but I am feeling some headache right now.
वो तो आएगा alignment
हाँ. Thank you, ma'am. नहीं चाहिए. Okay.
ये कुछ नहीं सर एक्चुअली मैं भी
हो गया चालू? और डायरेक्ट तुम YouTube वगैरह पे डाल रहे हो, मुझे बता तो दो, मैं तो हर कुछ बोलता रहता हूँ क्लास में। It's okay. It's working. All came. Proceed. Okay. Now, as per the Hilbert space theory, okay, the first mechanism we have understood that we can amplify the amplitude associated to the target states. That is the target quantum states. Now, another thing, the Hilbert space is allowing us to get the information related to the angle of the quantum states, that is the phase related information. Okay, the phase here we are considering to estimate the value of theta, because we do not know what is expanded or what is explored within the quantum system. We do not know anything about. Understood? अभी मत लो यार, फिर मैं पढ़ाऊंगा क्या? मुझे दिखेगा नहीं। नहीं अभी नहीं ना। अच्छा कर रहे हैं? हाँ इट्स ओके। नहीं वो तो हो जाएगा, देखना, लेके ही मत चले जाना, नहीं तो बताऊंगा क्या। ठीक है। चलो इट्स ओके। सो अंडरस्टैंड, देखना मुश्किल है। सो व्हाट वी आर वर्किंग हियर, दैट इज ऑन quantum phase estimation technique. So you first try to understand our quantum system, which has already been that is expanded with the some number of quantum states. Clear? So we do not know anything about that quantum states, but we are here to expect some theta or the phase related information which is associated towards every quantum state, because based on the theta value you may also be able to identify the amplitude related information. Clear my point or not? Because once we have just seen the Grover's interpretation, when we expanded our that is a superposition state, it is making an angle theta. Clear? So now look at here, that why this core phase estimation algorithm is required. This phase estimation algorithm is a subroutine that works in a Shor algorithm also. Shors that have proved the threat onto the classical crypto system in 1994 itself. He has given one period finding subroutine that is allowing us to get the period of a function in just a logarithmic computational times. Okay, for which the classical inefficiencies are always available. Okay, our classical machines are not enough. कर दिया? नहीं हुआ? वो आगे से गया ना, ठीक है, इतना तो मैंने कर लिया था, ठीक है, और ये हिला के ले आया, पता नहीं, एक मिनट रुकना। चलो ओके, लॉट ऑफ प्रॉब्लम्स है ना, बट थिंक अबाउट सॉल्यूशन, इट्स अ बेटर स्ट्रेटेजी, है ना. सो लेट्स एंगेज इन अ learning part. So now what's the next is, so this is the first thing, this is the first application that based on the QP the Shor algorithm can be implemented. Other thing is that the QP phase estimation that can estimate the eigenvalues of a unitary operator given its eigenvector. It's a main application here in our context, as well as this would be connected at the last topic of our session, that is a dimensionality reduction problem. Clear? So because that problem is considered as what? We are given with some matrix A. Just look at here. Okay. What's the problem? That we people are giving a matrix A, okay, with some vector x, and we are assuming that there should be some scalar multiples that is called to be an eigenvalue that is associated with that vector. So if some eigenvalues means based on some scalar multiples, the same vectors can be written down. Clear or not? So this is the basic concept which can be here done using the phase estimation technique, that is to estimate the eigenvalue of the unitary operator or to get the eigenvalue of this matrix operator A. Okay, which is the eigenvalue? Lambda. So lambda must be the eigenvalue associated to A. Okay, where we are just assuming that given vector should be an eigenvector. Okay, so now look at how do we just map this problem. The given A can be written as unitary operator here. Okay, this unitary operator can be supplied with what? Some quantum encoded state. This is the quantum encoding of the state. Like for dimensionality reduction problem, okay, we have what? We have what? That is a pre-CA as one of the core algorithm, that is quantum principal component analysis. The entire computation of that algorithm is based on the computation of covariance matrix. So what we will be doing that time, the covariance matrix like this X, that would be encoded here as phi. So but this phi is looking like here in a simple one, that would be the density matrix exponentiation. Okay, there would be a different aspect through which we can realize. Okay, now the fact is, what we used to call that when we apply this unitary operator on to the quantum encoded state, we are expecting some lambda that would be associated to the same that is quantum state, means this would be the eigenvalue of the unitary operator u. Okay, but the eigenvalue lambda associated to the unitary operator u would be written as implicitly e raised to the power of 2 pi I of theta. Understood? So 2 pi e raised to the power 2 pi, because already we are talking about a unit circle. Okay, so if we take the consideration of unit circle, we start from what? From 0, pi by 2, pi, 3 by 2 of pi, and next again 2 pi. So again our quantum state should start revolving around the unit circle. So based on that one, we are looking for that e raised to the power 2 pi I theta, because e raised to the power I theta we are known. This is the Euler's function, yes or no? E raised to the power I theta can be written as cos theta plus I sin theta, where this 2 pi is a factor included just to work upon the unit circle. Clear? So my vector can be anywhere on that circle, and each time their corresponding phase information would be different. Yes or no? Now how would you visualize the thing? You try to just do by your own. Like I am talking about the unit circle. Initially I am at the state 0. Now this vector is start moving. Okay, this is at pi by 2. Now pi. Okay, next 3 by 2 of pi. Next 2 pi. One complete round is done. Okay. Now similarly, if I am saying that a particular quantum particle is also following a wave-like nature, like I am starting with the sine wave, that is from 0. Now pi by 2, pi, next. So one circle, that is one complete round of what? Your sine wave. It is just similar like that one. So the concept is taken. What does it mean? Every point of time your phase related information would be different. Every time the phase would be different. The theta gets changing. Yes or no? So our problem is to estimate this unknown value of theta from the quantum system. That how do we get this unknown value of the theta, that is theta, from the quantum system? That is our target. Okay. So however, that QP is also used to estimate the eigenvalue of the matrix solving a linear system of equations like HHL algorithm. It is one of the dedicated algorithm in order to solve the system of linear equations. I will let you know in the machine learning part. Okay. Now the QP is used for the quantum counting purpose. Okay, this is several applications of QPs like quantum counting, but for what purpose we use for? Quantum amplitude amplification based Grover search we have done. But what the Grover did? The Grover did the finding of a marked state from the quantum system. Okay. But this was a hypothetical consideration what we already discussed. Hypothetical, I am letting you know again. We assumed that only one quantum state is satisfying the search criteria. But in practicality, this is not possible. Yes or no? For a particular item, there can be a several quantum states that must be satisfying the criteria. Yes or no? If suppose on a large unstructured database, if suppose I want to search for a number 2, so number 2 can be located at 10 different places. But out of all these 10 different places, my Grover's basic Grover algorithm is identifying any one of the random quantum state whose corresponding amplitude is becoming high. Understood or not? But what about the rest of 10? They should be identified or not? Yes or no? So this quantum counting is a routine that would let you know that how many particular instances of the same item are remaining present in the entire database. Understood or not? So this is one of the other perspectives. So application of a QPE, because without QPE this would not work. Okay. So now, so the problem is what? You are given with a unitary operator and with some encoded state. You will have to identify the corresponding eigenvalue and eigenvalue that is associated to the eigenvector. Okay. So and the eigenvalue can be encoded as, eigenvalue is encoded as what? E raised to the power 2 pi I of theta. Now look at here. So here there are some mapping. I am taking some mapping. So this QP is to find the unknown phase angle value of theta such that the eigenvalue of the unitary operator we find. Because if I want to get the if I want to get the information related to the eigenvalue, means I want to find lambda, okay, as a eigenvalue. So in order to get this lambda as a eigenvalue, the theta value should be known. Without getting the value of theta, we can't get to know about the lambda value. Okay. So like in an example, I am having a S. S is what? Phase gate. Yes? S is phase gate. Which phase gate? Pi by 2. Theta is pi by 2. So because the theta is pi by 2 here, okay, so S gate is a variable which is applied on one quantum encoded state. This is an example. So instead of phi, I am writing here 1 as a quantum encoded state, and I am looking for e raised to the power 2 pi I theta, okay, and the same eigenvector I am taking here. So if we can be able to estimate this value of theta, we can be able to get the value of eigenvalue associated to S. Okay. So what's the eigenvalue associated to S? S gate means the matrix operation is 1 0 0 I. Yes or no? So I means what should be the value of theta here? Now look at here. When we put the theta is 1 by 4. So this would become what? 1 by 4? 1 by 4 means it's e raised to the power I pi by 2. Okay. So e raised to the power I pi by 2 would be equal to what? I. So basically for S gate, target register. Because once you explore your quantum system, it would be comprising of all, that would be a tensor of all. It's really hard to understand what is happening actually within the quantum system. We can't know anything. Yes or no? Yes or no? Now tired? No. So what to say? I need at least a response from your side. Huh? Okay. I asked you to run the circuit. I asked you to run the circuit by your own yesterday. How many have done this? Please raise your hands. 3-4 people. Means my colleagues are not sincere. But it's okay. Thank you very much. But those who have done, and there is no like, अरे यार ये क्या है, ये बहुत परेशान कर रही है. चलो. Now, the other things related to the code, you are known. Let me just go with the composer again. Let me check whether I am in or not. Yes, I am in. Okay. Now, this is the 1 qubit system. Okay, and you are known that what to do. What to do, that is for x. HZX is the same output. Okay, so look, this is x. So when you apply x, okay, when you apply x, it is showing 1. Now here, state vector is available and quantum sphere is also available. Okay, so on a quantum vector, there is a checkbox. Okay, one is to show the state, that is with name. Another is the phase angle associated with the state. Clear? So now applying here a phase angle. So what's the phase angle here? 0. Because once you have applied, there is no change in the phase. It is only a bit flipping operation. Yes or no? It's a bit flipping operation. It is not a phase flipping operation. But if the same operation you want to apply onto the HZH, so let's check what is happening here. Still check. What's the phase? 0. Now apply H. This is H. Means it's a equal superposition. Okay. Again if you apply H, superposition lost. Yes or no? I told you superposition lost. Now in between them what we need to apply? Not. Oh sorry. No. Z. Where is Z? This is Z. Okay. Now this is Z. So once you apply this Z, if you see on the block sphere, the phase information is changed. And associated to which qubit? 0 or 1? We have demonstrated this thing yesterday. Okay, when you apply Z, there is no impact on 0. Only impact happens with 1. So the 1 state becomes red here. Clear? Now let's apply. क्या हो गया? अच्छा चलो. Now what to do? Apply what? H. So H, Z and H is giving you the value what? Equal to naught. But what about the phase? Phase is 2 pi. Earlier the phase is. So what's the difference? Difference is only in the phase value. But it would have no impact because it's a global phase. No such relativeness. Yes or no? We always look for the interference patterns based on the relative phase values. This is the global one, no problem. Yes or no? Still, because the resultant what we people are getting is the same. Understood or not? Yes or no? Yesterday we saw one more. Let me demonstrate. I have given you one assignment. Okay, assignment means to work out immediately. That is a swap gate. Swap gate is 2 qubit gate. Acha, you just look at one more thing. Right now how many qubits I have? 1. So if you see only 1 qubit I have taken here, so all the other gates which requires more qubit are already disabled. Can you be able to see this NOT gate disabled? that is C naught gate is disabled. Only single qubit gates are available. Once you add, you click on and you just plus. So once you add, 2 qubit gates are enabled. Once you add more, like still if you see CC naught gate, this must be like RXS, this is CC naught gate, it is disabled. But once you add again one more, all are now available, enabled. Clear? So now let me complete with what? The fact of a swap circuit. This is swap gate, yes. Now I am applying a swapping of information. Is there any visualization? No, because both are 0. 0 swapped with 0. Clear or not? So in order to check for this one, apply not on 1. So this is 0th initialized, means this is LSB. On LSB we are applying. Yes or no? So if you see here, this LSB, that is 101. Okay. So now here if you see, so after LSB, means let me delete it. First you see, this is what? 0, 1, because LSB is what? Rightmost. Okay, rightmost bit. So on the rightmost bit there is a LSB and we have applied 1 here. Clear? After that one, what to do? Now apply the swap gate. Now we have applied. So 0, 1 becomes 1, 0. Information is swapped. Clear? Clear? Now how I asked you to design the same? By apply C naught, again C naught in reverse. So like C naught in reverse, it is here in a COSM code you go to edit. Okay, C naught, here you take the control as 1 and target as 0. Okay, done. Now next again this as, so this is what? The circuit, but it is not swapping the information because our information is still 0, 0. Okay, so now what to apply? Not. So when you apply this not, you are getting the same value. Understood or not? So these are some transformations. Like this composer is suitable for you all to just drag and drop and just check what the circuit is doing, what the phase information is happening, how the state vectors are moving around over the block sphere. Okay, what's the probabilities, what the state vector amplitudes available in the system, what's the expected probability that should be outputted from the system, like these all things. Clear? So these things can be interpreted by your own. Now you know the fundamentals. Clear my point? Now you know the things, that how to go, how to proceed. Understand my point or not? Is it done? So shall we close this thing? Yes? So this is all this was about phase estimation approach. Mathematics we have already done, implementation done. These are some references related to what are phase estimation and Grover's algorithm all, and this is the end of this chapter. Okay, now a target is to proceed with machine learning part, है ना? Now it's 12:30 now, 30, 35, 45, अरे time भी नहीं दिख रहा है, 45, after 120, or right now we can take. I am waiting for my that specs also. So if it is convenient to take the lunch for half hour, so you just please go and take your lunch, because the next session would be really tedious for you all. It would be again fast because time is limited. Can it be possible? So 1 o'clock only. Chalo, let's proceed, otherwise no problem. No, I was expecting only, but okay, let's discuss with the theoretical part. Okay, let's proceed. You do one thing, this is one suggestion from my side, because now we are transiting from complete core fundamentals of the quantum computing towards the machine learning part. So we need context switching again. Task is being switched now, it's okay. So your processor should be known again. So you have your 1 or 2 minutes of time, then we will start, okay? Or if you are ready, so I have no problem. I have no problem, okay? चलो डन, मैं तो रेडी. हाँ चलो, it's okay. What happened, madam? अच्छा nothing. चलो, it's okay. So now the context is different. The topic is related to the quantum machine learning requisites. Okay, the requisite things to be discussed here is important. Why? Because for dealing with any machine learning task, rest of the fundamental related to the machine learning would remain same. Okay, I am not here to just let you know about, okay, what's the supervised learning, unsupervised learning, everybody knows. Okay, so everybody know these all things. The quantum computing part, that should be integrated in order to get the machine learning solution, that is to be discussed. And not all we can discuss, but the things which are requisites, okay, for every machine learning task, that would be discussing here. Clear my point? Okay, so as per the things we have already planned, this is as per the quantum data encoding, feature mapping, followed by what? That is a dimensionality reduction and a machine learning model processing. Okay, any model processing we will check. Okay, now look at. So outline of this session is containing a machine learning significance. Okay, that is quantum machine learning significance, followed by state preparation, data encoding methods, feature mapping, kernels, okay, machine learning and other essential things. Other essential things instead of data encoding and a feature mapping. What the other things you will require to think upon for transforming your classical machine learning solution into a quantum machine learning solutions. Clear?
Sir, shall we take lunch break now? Because you are suffering from...
No, there is no, it's okay ma'am, because it's I already requested. So if half hour of lunch you people may take, so you go and proceed, go fast, come fast, as early. 1:30? Sure? 1:30? So go fast. It's okay, go fast. From 1:30 to 4:30 I'll finish everything, don't worry. Huh? Go fast, come fast. कि भैया इसको वो करना है क्या तुम्हें?